So let's look at octahedral case only. So let's say we have this, right? And if we have this as x, y, and z, we can also draw it like, so I'm trying to draw it in a way so that it is easier to identify the C3 axis. So this is my x, y, and z. This is my minus z, minus x, minus y. Okay. And this is my C3 axis, which is now equidistant from all three and going perpendicular to the plane of the board if I've drawn it like this, right? So now if let's first do a C3 operation on XYZ. Okay. So if we have, let's say, let us make a table, do C3 operation, and we'll also do C3 square operation on X, Y, and Z. So if it is C3 onto X, X goes to Y, right? If we do C3 square, X goes to Z, Y goes to Z, and Y goes to X, Z goes to X, Z goes to Y. So that means X, any property which is oriented along X, Y, Z, that is Px, Py, Pz orbitals, that will be degenerate. So Px, Py, Pz orbitals will be degenerate under OH symmetry. Similarly, let us also look at d orbitals now. So if we want to draw, so we have dxy, dyz, dzx, and maybe here we will draw for the rest of the two. So dx square minus y square and dz square. So by the way, dz square is not the complete representation, so it is actually a short form. So the full functional form is 2z square minus x square minus y square. This will be required. C3, C3 square, C3, C3 square. So now what happens if you do C3 on dxy? How do you calculate that? So you don't need to actually measure that. You just need to see the effect of C3 onto X and effect of C3 onto Y independently, and you will get the correct answer. So X goes to Y here, so I'm reading from here, and Y goes to Z. So I can say if C3 is applied on dxy, I will get YZ. Similarly, if C3 square is applied, I will get ZX. Right? Similarly, again, C3 is applied on YZ, so Y goes to Z, Z goes to X. So I will get DZX and DXY. Similarly, DXY and DYZ. So now you can see that these three orbitals are interconvertible by doing one symmetry operations, a one symmetry operation or two symmetry operations. So this would mean that there is no change in energy between these orbitals, right? So that means I can say that these three belong to same energy, and these have same symmetry also, T2G symmetry. So we label this set of orbitals as T2G. Now let us look at this one. So C3, if you do on x square minus y square, you will get y square minus z square and z square minus x square. Similarly, if you do C3 on this, you will get 2x square minus y square minus z square, right? Of course, d. And here we will get z goes to y So 2y square minus y goes to x square minus z square. So I hope this is clear. So now it is not easy to see whether these two orbitals are same or getting interconverted or not. So but let us look at it more carefully, that we have also said that it could also be a linear combination of each other, right? So let's say if this particular orbital is a linear combination of these two or not. So let's look at this. So let's see one of the orbitals, which is 2x square minus y square minus z square, which actually is obtained after we did C3 operation onto dz square, right? Or 2z square minus x square minus y square. So if this can this be expressed as linear combination of the two d orbitals? So one is d 2z square minus x square minus y square plus b times d x square minus y square. And now we can just take the functions of this, because we want to see if the linear combination is there in terms of functions. So we'll just take the mathematical part. Y square minus z square equal to a 2z square minus x square minus y square plus b x square minus y square. Now comparing the coefficients of x, y and z, so we can say comparing the coefficients of x, y and z, what do we get? So we can say, if we look at the coefficient of x, it is minus a. If we look at coefficient of x here, plus b, and on the left hand side it is 2, right? Similarly, let's look at the coefficient of y. So we have minus 1, and here we have minus a and minus b. So we have two variables, two equations, we can solve it. So this gives us a is equal to minus half, b is equal to 3 by 2. So now we can say that this d 2x square minus y square minus z square is equal to minus half of dz square plus 3 by 2 of dx square minus y square, right? So similarly, other orbitals or other results of the symmetry operations can also be worked out, and we'll see that they will always form a linear combination of the two, right? So although it looks very different, but they are actually indeed linear combination of each other. So that means that we can say that these two orbitals will always have same energy, okay? I mean, at least in octahedral field. So now let us see why EG set of orbitals. So these are EG set of orbitals, right? These are EG set, and the other triplet is T2G set. So why EG set of orbitals increase and T2G set of orbital relatively decrease in energy? So let's say if we place a transition metal ion in spherical field. So to start with, it was a isolated ion. Now we are putting it in a spherical field again. So again, R3 to R3, right? So initially, symmetry of this metal ion is R3. Now spherical field will also have R3 symmetry, that is spherical symmetry. So that means there is no change in relative energies of different d orbitals, T2G and EG set. It will not break into T2G and EG set because R3 does not have any such IR representation called T2G or E3. So all 5 d orbitals will continue to remain degenerate, but there will be an increase in energy. So why there would be an increase in energy? Because now imagine that there is an electronic field which is coming because of the ligands, surrounding ligands, and now there would be a repulsion in the valence electrons with the valence electron of the central or the transition metal ion and the spherical field which is created by ligands. So that repulsion will increase the energy of those d orbitals. So we can say that the energies of all 5d orbitals would rise together. This is if it is placed in a spherical field, and this happens as a result of repulsion of negative charges of the ligands repulsion, we should say repulsion between, right? Repulsion between negative charges of ligand and negative charges on the electrons in the metal ion. Okay, so now imagine that instead of spherical field, now we have octahedral field. So how do we get octahedral field? So we have, let's say we have 6 ligands, 6 approaching ligands, and all of them have to be equidistant from M plus central metal atom, right? Now if they all have to be equidistant and they all have to minimize ligand repulsion, then we can imagine that the what we can imagine the ligands are approaching via coordinate axis. So of course this is true when you have this is only an assumption, huh? So when you have metal atoms sitting at the origin, let's say, and these are your coordinate axis, so ligands are now coming from these sides, because that way it will be equidistant from metal atom and also equidistant between each other. So the ligand repulsion would also be minimized, and there is no preference of one ligand over the other because all of them have to form similar bonds, right? So this happens in octahedral case. Now, so why Eg set of orbitals would increase in energy and T2g set of orbitals will decrease in energy? So let us see the case for that. So now if you think that, let us first talk about Eg set of orbitals. So Eg set of orbitals, one is dx square minus y square, another is dz square, right? So how do I draw dx square minus y square? So you have these are lying along the axis, right? This is my x minus x, y minus y, z minus z, and these are my positive lobes, these are my negative lobes, right? Okay, so now if you see that the ligands are approaching from coordinate side, coordinate axis, 6 ligands, and now there is a direct interaction between these orbitals and this the ligands, incoming ligands. So other than Z, all of them are oriented direct head to head, right? And similarly for dz square, what happens? So you have, so here also the ligand is now coming, one from this side, another from this side, right? So idea is that there is direct interaction between the orbitals and the ligands, and because both of them are oriented along coordinate system, of course this is a imaginary thing that both of them are oriented along coordinate system, but this is just for, like, you can take any other combination without having to imagine that this is actually oriented along coordinate system, but you will still find the same answer. Okay, so this would mean that there is more repulsion between eg set of orbitals and the ligands, so that means there is relatively more increase in energy of eg, right? So now if I try to draw the same thing for, let's say, dxy orbital, you should be able to appreciate that it is not oriented along the axis. So it is oriented somewhere in between, right? This is my dxy, let's say. Similarly, dyz and zx will also be there. But the ligands are still oriented along. So this would mean that my energy level diagram would look like this. So I have R3 symmetry, and I have these two orbitals are increasing in energy, dx square minus y square and dz square, and three orbitals are decreasing in energy relative to this. So you have dxy, dyz, dzx. Now this happens when it is octahedral. Now similarly, you can also think of tetrahedral case where this order gets reversed. So why this order gets reversed? So if I try to draw tetrahedral field around my isolated central atom, my metal is still sitting here at the origin, and now if I try to draw, how would I draw it? So I'm drawing a cube around this thing so that drawing a tetrahedral atom would be easier. So now my ligands are, there are 4 ligands now which are approaching from these sides. These are my ligands, right? This is my metal, and L1, L2, L3 and L4. Now if you see that the ligands are not approaching from the axis, but they are approaching in between, right? So if I say that this is my, let's say if I try to draw dx square minus y square, only 2 lobes will have direct interaction. If I, this is my dx square minus y square. Whereas if I draw dxy, all 4 lobes will have relatively more interaction with these ligands as compared to dx square minus y square, right? So I can say that in tetrahedral field, the order is reversed. So I have dxy, dyz, dzx, and dz square, dx square minus y square. Okay. So of course, overall delta would also be different in TD, tetrahedral point group, versus octahedral point group. So which delta would be higher, which delta would be lower? So if you see that here the interaction is stronger because there are more ligands which are oriented along coordinate axis. So interaction between the orbitals and the ligands is much stronger than the interaction here. So that means the change in energy or the perturbation is also higher in OH. So this delta, I will say delta OH, and this I will say delta TD. So relatively speaking, delta OH will be higher than delta TD. Of course, the order will also be reversed, but there would also be another difference, that delta OH will be higher than delta TD. Okay. So, of course, if you have to calculate the exact energy, so we will just write down that. So, exact energy requires setting up of secular equation and solving all the integrals. Whereas group theory will give you relative idea of which energy would be higher, which orbitals would be higher in which particular field, and so on. Okay, so relative energies are described by group theory. Okay, so we can say relative energies only. So we can only talk about relative and not the exact energies, right? All right. So I think this finishes first lecture on crystal field, and we will see more that how do we explain Yon-Teller distortion under different fields in octahedral or in tetrahedral, wherever it is there. So we will see all of this in next class. Okay. So that's all for today.